some of the ideas. I just very briefly, before you see the film's more interesting than I am, share with you some of the ideas, because when they come at you, it's kind of, well, I've heard these things and I don't really know what they mean. So, I mean, I just looked at the title and I thought, theory of everything. Why is there a theory of everything? Why are physicists always worried about a theory of everything? So, you know, in my little world, you know, we're here, and everything should involve the cinema, it should involve this film, and it should involve all of you, all of us, we're alive, and that should be everything. But that's not what a physicist means. Oh, no, the physicist thinks that that's some kind of just consequence of the bigger everything, which is the universe. And so when a physicist talks about the theory of everything, they're talking about the theory of the universe. Now, there's an element to which that is changing, and I will talk about that at the end, and even Hawking himself says that. But let's look at the theory of the universe. So in some sense, the theory of the universe, of course, is very hard. You know, lots of particles and explosions and all these kind of things. But in some sense, it's really easy because it's like a closed system. So it's like, in some sense, what physicists do, they look at the universe now to try and work out what happened way back. So it's a little bit like and I don't know if you've ever had this, but I have some teenage kids, and so I do have this a lot. You come home and something's gone on, and you know there are a few elements you can see around that indicate something might have gone on. There's a broken plate, you know, there's a lot of stuff in the trash bin, and you know, and you say to them, what happened? Oh, nothing. No, somebody, there were people from outside came in or something. The universe isn't like that. There is no outside. There is no outside. So everything you see in that room when you come home, it must have been caused by the people there. Well, in the sense of the universe, it's caused by the objects in the universe. So the nice thing about looking at the universe as a whole is there is no outside. And so what do physicists do? Well, they look at everything that they can see. Now, here's the deal. We're seeing something like, well, I don't know, 4th of July, we see fireworks, you know, in New Year, it's, you know, I spend a lot of times down in Colombia in New Year, you see, you know, voladores, fuegos out, and you think, wow, where did that come from? You see it in the moment of the explosion. You didn't see it go up, you didn't see it explode, you didn't see the person prepare it, you just see the remnants, and they're beautiful, of course, you know, you see bits flying off in different directions. Well, that's exactly what we look at, or physicists look at, when they look up at the sky. You see the remnants. And, you know, like a logical thing, you see them flying off in a certain direction. It's natural to kind of try and wind the clock back. You know, where did they come from? And you wind the clock back, and you know, even if you did it for a firework, you wind it back. Yeah, you think it kind of came from one place. Because your eye sees it spread out, so it came back from one place. So that explosion, you know, it's some tiny region there where everything exploded from. So that's, if you believe that these things are flying off just like a firework, that would be where the universe came from. One tiny little region of space. Okay, so that sounds hard to try and work that out. But here's the problem, and it's a bit of a bombshell. Space is not independent from time. Now, let me just unpack that sentence, because that's a pretty deep sentence. Space, if I roll back, you know, what's happening with a firework, it comes from one particular place, an explosion. Yeah, that may have been at like 7:15. Well, there may have been an explosion before at 6:45. And in fact, it didn't really matter when that explosion was. The same thing happens. It explodes, things come out, we wind the clock, you know, in our head, we think, yeah, it came from there. It doesn't really matter when it happened. It could be Monday, it could be Sunday, Thursday, it doesn't matter. It's just the evening and there's an explosion. That's not how it works in physics. And the reason it doesn't work like that has something to do with, or at least the way I'm going to explain it, something to do with, well, is anyone here like football? And I mean real football, football with that shaped ball, not, you know, so it's not, messy soccer, it's football. Anybody here like football? Yeah, the same number of people who like physics. I'm not sure it's the same people who like physics, but anyway, same number of people who like physics. Wide receivers, wide receivers. Everybody knows what a wide receiver is. Quarterback throws, and I'm not going to try this because I'm useless at it, but if the deal with a wide receiver, which is, maybe what the Dolphins need to sort out, but the deal with a wide receiver is if the wide receiver runs fast enough and the quarterback throws it just right, then the wide receiver will be running, and I'm not sure I could do this, be running, and as he is running, the ball will look to him as it's coming in, and it's not moving with respect to him. Relative to him, it is not moving. That's the whole deal of a good wide receiver and a good quarterback. You throw the ball, and the wide receiver runs as fast as they can, and the quarterback has pitched, that tells how much I know about football. I nearly said pitched. Thrown the ball at such a speed, exactly the right component of speed, so the wide receiver sees it coming in relative to them at zero speed. I mean, of course, it's coming towards them. That's the whole point. So the wide receiver is effectively just catching a ball that's moving towards them. It's not running away from them, and it's not behind them. That would be a bad throw. Okay, here's the bombshell. That's not how light works. If you were catching light, that is not how light works. If NFL football was run with not throwing a ball but throwing particles of light, I'll get onto those in a minute, particles of light, that wide receiver would never be able to run fast enough to catch up. Because the deal with light this is Einstein's special theory of relativity, as much as you run or as much as you move, or you can move in the fastest rocket that's existence and then build one that's twice as fast, 10 times as fast, 1,000 times as fast. Light will always travel at the same speed with respect to you. So that's a problem, because what it means is that space, actually, as you think about space and time are going to be coupled. Why is that? Why would they be coupled? Well, I've just said that there's something that has a speed, a particular speed of light, that doesn't change. It doesn't change with respect to you. So if you think about driving, if you drove down US 1, coming here, you were going at 30, or hopefully you're going at 30 or 40. Maybe I shouldn't be going at 30, I should be going at 40. But anyway, whatever speed you were going at, you were traveling a certain distance per unit time. So, set on your clock, 30. Officer, I was only going at 30 miles an hour down Granada. You were saying to the officer, 30 miles in 1 hour. So here's the problem. Speed, I just said speed of light, is constant for everybody. Doesn't matter if you're running, you're walking, you're on a supersonic jet, doesn't matter. This is a problem because it means that if the velocity is speed is distance over time, that means as we change the distance, we have to change time. As we change space, we have to change time. And we just said that the universe came from some really small region of space. So something happened. It must have also involved something really small in terms of time. In fact, really the beginnings of time. This was a huge problem for when people started to think about the origins of the universe, and I need to illustrate another problem, because bombshells in physics tend to come in threes. Here's the second problem. If we think about, so we've got space and time coupled. If we think about light as particles, which they are, another thing happens to objects, particles, balls, any kind of ball. If I drop them, they fall. And the reason they fall is because there's gravity. And if light is consisting of particles, it is attracted to objects that pull it due to gravity. So suddenly we've got space is linked with time, and time is linked with gravity. Now, those three, the combination of those three, you'll see Stephen Hawking grapple with for a long period of his early work. How do you link together space, time, and gravity? But there's another bombshell. This is the third one. So we had the first bombshell that space is linked with time, therefore it's space-time. We had the second bombshell that there's also gravity involved, and so gravity pulling on particles of light and therefore changing the path of light well, light's meant to have a certain speed, so if you change the path of light, you're changing where light's going, you're probably changing space and time at the same time. That was the second bombshell. Third bombshell. When you get down to the small scale of distances or times, something else comes into play called quantum physics. Now, we always think of Einstein as being famous because of relativity. We just talked about the theory of relativity. It's the wide receiver looking at the ball, but if it was light, he could never catch up with it because the speed of light is the same no matter how you're moving. It's not, that's Einstein's theory of relativity. But Einstein actually won his Nobel Prize for quantum physics. Quantum physics is the idea that, well, actually light is made up of particles. And if light's made up of particles, then it's going to behave, these particles are moving around at the speed of light, then we've got some very strange connection between the energy and space and time and gravity. Einstein won his Nobel Prize for just saying that light was made up of particles, but he never accepted the fact that the consequences of that mean that somehow it should be inserted into his theory of relativity. He never did that. He never managed to do that. Hawking tries to do that. He gets some way with it. In fact, a lot further than a lot of other people. But that is the dilemma at which physics is. Space, time, gravity, quantum physics. And nobody has really managed to connect those things together. And I'll just give you a couple of the ideas, one of which is Hawking's idea. Let's think where, I go back to the universe being like this firework coming from this very small region of space. It now, as you know, comes from a really small region of space and time, and it also comes in a kind of quantum form. So Hawking described this as a so-called singularity. A singularity is those things that, in my everyday life, I get a singularity when I try to iron my shirt, as you may see if you were to get very close. Singularity is when you start to try and smooth things from one side and you smooth them from the other, and there's always that annoying wrinkle in the middle. That's a singularity. Or if you don't like to iron shirts, which I often don't, just think of when you're trying to put one of those annoying covers on your cell phone and you smooth it out from one side and you smooth it out from the other side. And where did that bubble come from in the middle? And I can't get that bubble. That's a singularity. That's a singularity. Now that singularity is that small region of space and time where the universe started. So everyone's now trying to argue what happened in that little bubble. So there are a few kind of theories of that, one of which is Hawking's that you'll hear about, the no boundary theorem, which says, actually, if you go inside that bubble, it's like another world. It's like another world, and there is no start and finish of, when everything happened. It's like going to walk. If you walk to the North Pole, and I gave you instructions, you wouldn't want to do this, but I gave you instructions, just keep walking north. Eventually you'd get to the North Pole, and then you'd stop walking north. You couldn't walk north. Now, going north had suddenly ended, but it wasn't like there was some big spectacular there for you, or some great big, wall or, celebration or party or something. No, you just keep walking, and there's nothing there, but then suddenly you're going south. And that's the no boundary theorem of Hawking. It says that, there's no boundaries on time. You just keep kind of going round. But there are other theories. I should just mention those two. There are many others, but they fall into two kind of genres. I mentioned about quantum physics. So one thought is, actually, if you want to get down to the boundary of time, of going back in, looking at this region, going back in time, going to go back to where the universe started, it's a bit like getting closer to the surface of the sea. From a long way away, it looks like there's a hard boundary. But as you get closer and you get down to the surface of the sea, it begins to become frothy. There are bubbles there. There's no surface of the sea. There's a bit of a wave, and there's a frothy bit here, and then it goes. You couldn't actually define where the sea stopped. It'd be really hard. It's kind of just frothy bubbles. And that is a quantum picture of how time started. And then the third idea of what goes on in this singularity, in this wrinkle of the shirt, is the idea of a Groundhog Day. You won't hear Hawking call it a Groundhog Day, but he toys with these three ideas, and you can just about hear them during the film. Groundhog Day is what goes around comes around, that the universe will just ends and starts again in another Big Bang. And the thing just keeps going on. I'm not sure if that means the Big Bang Theory series starts all over again, but it's certainly the Big Bang starts all over again. So that's the situation. You're going to see the film. I'm going to shut up in a minute. But I want to tell you something that they don't show in this, but I guess if there was a Theory of Everything Part 2 sequel, would appear in that. And that is that in recent years, Hawking has turned around and said, well, actually, I think the 21st century, and this is not a plug for the particular research that I do, but I think the 21st, this is a quote of Stephen Hawking, I think the 21st century is the century of complexity. Because it brings us back to this idea that, well, everything isn't just the beginnings of the firework. It's the colors that came afterwards. It's the things that span off. It's the total thing. More is different. More is different. So it brings me back to what I started with. Everything for us means the cinema, the film. It's all of us, our lives, everything. And that really, in some sense, is what the theory of everything should be able to predict, but does not.